When it came to working with gases in the early 1800s, many chemists dreamed of a simple equation that detailed the relationship between a volume of gas and its surrounding environment, such as pressure, temperature, and volume. It was their holy grail. Luckily, this holy grail proved to be obtainable. Using other previously discovered principles like Boyle's law, discovered in 1662, Charles's law, discovered in 1780, Avogadro's law, discovered in 1811, and Gay-Lussac's law, discovered in 1808, it was possible, almost 2 centuries after the first component was published, for Émile Clapeyron to derive the ideal gas law in 1834. And it was perfect, so long as you ignored a few minor details like intermolecular forces and the atomic volume of gas molecules. 2 assumptions are made when using the ideal gas law. One is that the gas particles do not have any forces acting on them, including forces from each other, and 2, the gas particles do not take up any space within the sample. These assumptions, which define ideal gases, keep things simple. It should be noted that as the volume of the space the gas is contained in decreases and/or the temperature of the space decreases, the gas strays from acting like an ideal gas and starts beginning to act like a real gas. But we won't be talking about real gas properties in this video today. The ideal gas law contains 4 variables and a constant: volume, pressure, temperature, number of moles, and the gas constant itself, R. R, the gas constant, is merely a conversion factor that allows us to relate the variables in our chosen units. The gas constant has many forms depending on what you need. With the constant, you could have pounds per square inch, Fahrenheit, Celsius, any units that you might need, and it'll work out. With this, it's possible to derive any of the 4 previous laws, as well as any other equation you might need, and understand the relationship between the 4 variables. There are many examples of the ideal gas law at work in the real world. The most easily demonstrable is the act of breathing. As your lungs increase in volume, pressure proportionally decreases, and fresh air from outside is drawn in due to the pressure imbalance. The reverse is true when exhaling. As the volume decreases, pressure increases, and air is forced out of the lungs into the outside world. Compressed natural gas draw-off is another good real-world example of the ideal gas law. Compressed natural gas is increasingly becoming a gasoline or diesel substitute for high runtime transportation engines, such as taxis, delivery trucks, and buses. It is a much cleaner fuel than traditional diesel or gas, and produces much less greenhouse gas emissions. This gas is stored at up to 3,600 pounds per square inch at incredibly high pressure. For the gas to be used, this pressure must be decreased with a device known as a gas pressure regulator, which drops the pressure to a much more manageable 60 to 150 pounds per square inch. This regulator basically acts as a very durable opening, through which the gas can escape at a fixed pressure. This pressure is much lower, and the volume is much greater, but the amount of substance flowing is still the same, so temperature decreases to the point that the gas can actually condense into a liquid. This is solved by running engine coolant through the regulator and heating it. Another real-world application of the ideal gas law is in the design and regulation of pressure vessels to accommodate temperature changes. Common industrial gas cylinders may be 3,000 pounds per square inch or more inside. If the cylinder is heated after being filled, it may exceed this. This was demonstrated in 2005 in St. Louis in dramatic fashion. Cylinders were stored outside during a heat wave filled with highly flammable gas. As the pressure increased and the temperature increased, they began to vent, found an ignition source, and caught fire. The entire facility and several homes were destroyed. Luckily, no one was killed. Understanding of the ideal gas law enables us to make advancements in transportation, material storage, refrigeration, engine design, and so much more. From preventing gas pressure regulators from freezing, to keeping food cold on the hottest days, to understanding airplane cabin pressure, most of the basic conveniences of modern life derive from this fundamental understanding of the universe. Thank you for watching.